Thermodynamics, a presentation by Arthi and Sommer. Temperature versus heat. Temperature is the random motion of a substance's particles, while heat involves the transfer of energy between two substances due to a temperature difference. The Maxwell-Boltzmann diagram shows that as the average temperature of a substance increases, so does the kinetic energy and temperature range of the molecules. Enthalpy is equal to energy flow in the form of heat. So, when solving for the delta H, or the change of enthalpy, you can do the enthalpy of the products minus the enthalpy of the reactants. H is equal to E plus PV, where H is the enthalpy, E is the energy, P is the pressure, and V is the volume. This equation is formed from the combination of delta E equals Q plus W, where Q is heat flow and W is work, and the equation W equals negative P delta V. Enthalpy is derived from the manipulation and combination of these equations. Now let's take a look at the bond length graph. As the distance between two atoms decreases, so does the potential energy in the bond. In 1, you can see that the longer bond length distance results in a higher energy level. As the atoms continue to approach each other, there comes a point when the two nuclei will start to repel one another, which is what happens in 4 and causes a spike in potential energy due to that repulsion. The distance where the forces of attraction and repulsion balance and result in the lowest possible potential energy, as shown in 3, is known as the optimal bond length. Calorimetry is the amount of heat absorbed or released during a physical or chemical change that can be measured, usually by the change in temperature of a known quantity of water in a calorimeter. Important units include the joule, which is the SI unit for measuring heat, and the calorie, which is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius, and 1 calorie is equal to 4.184 joules. To measure calorimetry, this is the typical setup. A physical or chemical reaction will take place in a container called a calorimeter, which is unlikely to absorb or release a lot of heat. The components undergoing the reaction are surrounded by water, if the water is not involved in the reaction, and water temperature is measured throughout the reaction. Based on the temperature change of the water, we can calculate the enthalpy change of the reaction. Heat capacity is the amount of heat absorbed per degree increase in temperature, where the amount of substance is not taken into account. Specific heat capacity is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, and it is unique per substance. Specific heat capacity is also more useful during calorimetry calculations. The formula used to calculate energy transferred is Q is equal to mc delta T, where Q is the energy transferred, m is the mass, C is the specific heat capacity, and delta T is the change in temperature, which is found by subtracting the initial temperature from the final temperature. Here is a practice problem using the formula that you just learned. Please pause the video now and you can practice solving the problem. The correct answer is approximately 5,020 joules. The work shows how to correctly plug known variables into the equation and algebraically solve for the unknown, which was Q. Endothermic reactions. These types of reactions are characterized by energy flowing into the system as the reaction proceeds. The products of these reactions have weaker bonds since these bonds have a larger amount of potential energy stored in them. In this case, Q would have a positive value because energy is added to the system. This graph shows that after the reaction is complete, The products of endothermic reactions possess more energy than the reactants did. Exothermic reactions. These reactions are characterized by energy leaving the system during the reaction. Potential energy stored in chemical bonds is converted to thermal energy, released as heat, when the bonds are broken. The bonds in the products are stronger than those in the reactants because there is less energy stored in them. In this case, Q would have a negative value because energy is released from the system. This graph shows that it is necessary for the reactants to absorb more energy, known as activation energy, in order to break their bonds and begin the reaction. However, at the end of exothermic reactions, the products of the reaction exist at a lower energy level than the reactants did. Thanks for watching!